The greatest discoveries of humanity have their root at the academic institutions, where the culmination of efforts has been transferred to industry, who take it to the next level by producing products that are beneficial to the humanity as a whole.
Here at the Center for Polymers and Soft Materials at the University of Alabama, we focus on two things. One is to develop and synthesize innovative new polymer materials with properties such as self-healing. And two is to find uses for plastic waste and prevent it from entering the environment and causing problems for people and nature. So having the 3D-Bioplotter allows us to combine those two opportunities and accelerate our research. The material development came from a class of charged polymers called ionines. We can insert these charges into a polymer backbone that actually is very familiar to many of the plastics that make the world go around.
This combination of alternating forces pulls the material back together and enables this pretty rapid self-healing process to occur, regardless of it being a puncture or a cut.
And so it's really the synergy between the ions and the hydrogen bonding that allow this material to pull itself back together after it's been punctured or cut, so that a healed material behaves just like a material that was freshly 3D printed.
These reinforced self-healing polymers could really be helpful in aerospace and automotive industries, because ultimately our goal is to achieve parts with higher strength and lower weight.
7 years ago, I got connected with a researcher at NASA who was very interested in self-healing polymers. And I said, this is a perfect fit because this is exactly what we've been doing. So we worked together, and NASA helped get us some funding to develop the materials, and it allowed us to purchase the 3D-Bioplotter, which is really the only option for the kind of research that we wanted to do.
The 3D-Bioplotter allows us to process these new materials and really start pushing them from research stage materials into industrial sectors where these materials would be very successful.
I love the amount of material it could handle, the controls, the temperature range. Also, there was flexibility for us to work with softer materials without having to modify or change out a whole bunch of parts.
And being able to directly take that raw virgin polymeric material and immediately be able to process it into fibers or into actual prototypes is an extreme benefit.
NASA has always been interested in 3D printing, because when you go into space, you don't know necessarily what you're going to need or when you're going to need it. With the self-healing material, I should be able to bring it up into space and then make what I need. And when I'm done with that, I can break it back down, put it back in the 3D printer, and then make the next thing and keep that cycle going.
We are in an age of exploring the interplanetary systems. If your spacesuit is protected by a self-healing polymer, it is possible to decrease the impact of debris or dust particles coming our way.
And again, the only real way I see in space to make what I need to avoid these accidents is through a 3D printer. Because when you don't have a 3D printer and you can't make the right form factor of the material, things that seem easy are actually quite challenging and only enabled through a 3D printer. So having the 3D-Bioplotter has really opened up the possibility that any polymer we make can now be 3D printed.
The 3D-Bioplotter certainly elevates the research that is done here in the PolySM Center, and it serves as an excellent example of using cutting-edge technologies that really allow us to advance knowledge as well as research spaces that are underexplored.